Hey everyone, continuing our adventures in integration techniques, we'll learn how to integrate fractions of the form hx over gx dx, where h and g are polynomials. Alright? So basically just algebraic functions, and there are many possibilities where h is actually have a higher degree than g, but we'll start off simple first. So if you recall, what are the integrals that involve algebraic fractions, right? So the first two that should come to mind, alright, is actually both the GPR, the general power rule, and the logarithm, right? The general ln rule. Alright. Why is that so? Because if you look at the GPR, right, we have the following form of f prime x over fx power n. And then obviously you will then be able to integrate this, right? Same thing for general ln rule. Instead, it's now more specific. It's f prime over fx strictly, and then this will give us ln fx, right? So these two forms are integrable, and we should try to aim to have these two. But in some cases, right, we can't get purely these two forms. Sometimes you realize you'll get a mix, and therefore we might have to introduce this, all right, as a third, fourth, and fifth form. So we have third possibility, the fourth possibility, and the fifth possibility of 1 over x squared plus a squared, 1 over x squared minus a squared, 1 over a squared minus x squared. So as you realize that you might have to involve like certain other skills as well, such as partial fractions and your long divisions. But for now, we'll keep it simple first. And we just start with a very simple example. Let's say we have x plus 1 over x squared plus 4x plus 7, okay? So, how do we actually go about solving this first? The first technique that I like to do, right, is always go by the first two forms. Always try to reduce it to the first two forms if possible. So, if you look at the general power rule, right, for instance, notice that there's probably no way out, right? Because if you try to factorize this there's actually no way to factorize this except for x squared plus x plus 2 whole thing squared plus 3. Okay, so clearly this can be the general power rule because the denominator is not purely of the form ax plus b power n, right? So this will come in handy, just not now, okay, but soon enough. So we can't use the general power rule for this case. What about the general ln rule? We notice that the numerator has a degree that is 1 less than the denominator, right? The denominator has degree 2, the numerator has degree 1. As such, we can use the general ln rule. Just that, if you notice, fx is x squared plus 4x plus 7. So f prime x, if this is f prime x would be 2x plus 4, right? But here we have only x plus 1. So if you try to add a half a constant times a half constant, we will only have x plus 2, which is again 1 short, right? So what do? Well, we just add a constant. Alright, so now we have x plus 2 over x squared plus 4x plus 7 minus 1 over x squared plus 4x plus 7 dx. Okay? So now it's very simple. We are able to realize that this is just simply going to give us half ln x squared plus 4x plus 7, right? Because the numerator is half the derivative of the denominator. So we just add a half, right? And then it's just a form f prime over fx. So it's this half f prime, then bottom is fx. So we just add half ln x squared plus 4x plus 7. Okay. However, for the other one, what do? We know we can't use the general power rule. There's definitely no ln rule because the degree on top is 2 away from the degree below. So what do? So now what we do is we simply convert to this final form. All right. So the general idea of solving fractions of these types is that first you try to find a way to get it to the general power rule or the general ln rule. Most of the time it's the general ln rule. All right. Then manipulate it such that you are able to integrate into a ln function, but then obviously you'll be left with the remainder, right? Of in this case is 1. So what do you do with the remainder? Well, you convert it to either of these forms, okay? So it's very simple. now we try to convert this to the other form. So earlier I already showed you the conversion, right? It's this denominator is basically x plus 2 whole thing square plus 3, and then obviously the dx. So what do you do next? Well, our ln still stays the same, but based on the formula here, it's basically 1 over a. So we notice that our a square here is 3, so a equals to root 3. That means you get 1 over root 3 tangent inverse x plus 2 over root 3, not forgetting your plus c. Alright, so the general rule of thumb when it comes to solving fractions of these sorts, alright, prioritize the first two first. Try to get these two, try to force the form into these two. So as you can see, I have x plus 1, right? But then I realized, okay, it can't be GPR, so scratch that. Now we look at whether we can get to the general ln rule. Then we notice that if I let my denominator be fx, my derivative of fx would be 2x plus 4. Obviously, there's a common constant, so I change it to half, okay? Because that's what my numerator is. My numerator only has x. Therefore, with the x, I need x plus 2. So I need to add 1 more so I can get to a ln. Then I left the remainder because I added 1, I need to minus 1. So I minus 1, I get 1 over x squared plus 4x plus 7. And then afterwards, what I do the remainder will be these steps. Alright? So this is the general idea when it comes to solving hx over gx. So this is the first example where I showed you that the above is actually a degree lower than the denominator. However, there will be times where I have hx over gx, but the degree of h is actually bigger than the degree of g. So for example, let's say I have integrate x cubed plus x squared plus 2x plus 3 over x squared plus x plus 1, okay, dx. So clearly you want to get clearly, there's no way to directly integrate this, right? There's no such thing as a f over f prime because there's clearly no integral for that. So what do we do? Well, you wanted to convert it back to the first 5 forms, right? Because you notice that when the degree on top is lower than the degree below, you're able to kind of like find a way to integrate it, right? Through making it to a long function or making it to a power rule function, and then afterwards taking the remainder and then using the tangent inverse of the ln in formulas in the MS26. So how do we get the numerator to be lower than the denominator? The answer is that we must perform long division. So we have x cubed plus x squared plus 2x plus 3. Okay, if you're good at this, you don't actually need to do this, but I'm just going to show it to you guys. So firstly, get rid of x cubed, so I get x cubed plus x squared plus x. Okay, everything is perfect. I'm left with x plus 3. Alright, so now I know that my function will be converted to x plus 3 over x squared plus x plus 1 dx. Okay, now it's very simple. X becomes, well, x squared over 2. So that's the power of why you should long divide your algebraic functions if the numerator is big, if the degree of the numerator is larger than the degree of the denominator. What about for the rest? We apply the same techniques here, right? X squared plus x plus 1, so I'm going to force feed this into the ln function because there's clearly no general power rule at the bottom. Even there was, I think it wouldn't help. X squared plus x plus 1, so if this is my f prime would be 2x plus 1. What do I notice here? My coefficient of x on the numerator is just 1. That means I need times a half, right? So after multiplying by a constant half, I'm left with x plus half. That means over here, I just need x plus half to get me my ln function, right? Because I have x plus 3 originally, I need to add a 2.5, right? So you can just rewrite it in decimal form, it's easier. Plus 1 dx, okay? Thereafter, keeping the x squared over 2, then I already figured out that x plus half is basically half f prime, so I get half ln x squared plus x plus 1. Now I'm left with the 2.5, right? To 2.5 over x squared plus x plus 1. So going back to the favorite tree, right? So I'm just going to cover the, where should I put it? I think maybe over here. I think we don't need this anymore. Okay, so now we realize that, okay, for this form, we're going to convert it to either x squared plus a squared or x squared minus a squared, right? So let's do some completing the square. So the coefficient of x in the denominator is just 1. So that means I get half, right? Because it's always of the form x plus 1, x plus, so because, x plus a squared give us 2ax, right? So a in this case will be half. So half square is 1/4, that means I'm left with 3/4 outside dx. Okay, then now it's pretty simple. My final derivative is simply x squared plus half ln x squared plus x plus 1 plus, so I'll keep the 2.5, so 2.5, this is the form of 1 over x squared plus a squared, so a over here is root 3 over 2, right, because a squared is 3 over 4, so a is root 3 over 2, so I have root 3 over 2, that means I'll times 2 on top, tangent inverse x plus half over root 3 over 2, so root 3, then I times a 2 on top. And then obviously I'm not going to simplify this because I think I ran out of space, but you get the idea. The whole idea should be that the final derivative will simply be x squared over 2 plus half ln x squared plus x plus 1 plus 5 over root 3 tangent inverse 2x plus 1 over root 3 plus c. So this is the whole generic idea of solving of the function hx over gx. Alright, so in summary, this is the steps that to take. Alright, so you have hx over gx, right? Okay, obtain, so the first step is obtain a form, a fraction where degree of h is lower than the degree of g. Alright, through long division, if necessary. Okay, if necessary. Alright, I mean, if you see from first example, we will notice that the first example, the degree of the numerator is lower than the degree of the denominator. Next up is to find GPR, or more commonly G ln R, right? General ln rule. Afterwards, the remainder is to use this tree form. Find whether distinct form through completing the square. Complete square. Alright, so this is a general technique for hx over gx, and I hope that there'll be more examples to come. Of course, there'll be times where hx over gx, right, you get a partial fractions as well, so through long divisions or through partial fractions. Alright, for the partial fractions example, I'll put in the next video, so don't worry about that. But for now, this is the general idea.